There's two other types of stereoisomerism that we need to talk about. One is a concept called a diastereomer. So diastereomers are simply stereoisomers that are not enantiomers. So that's it. Don't complicate this definition. It's easy to do so. We're going to see some examples as we go through and look at some problems. And then the other one is meso. So meso is when we have two or more chiral carbons or chiral centers, but the overall molecule is achiral. So let's take a look down here below. Remember, one of the things that we can look for is we can look for a mirror plane of symmetry. And if we can find that in a molecule, then the molecule itself is achiral. So right down the middle of this molecule here, this is a Fisher projection. This is a mirror plane. So we expect this molecule to be achiral. However, it does have two stereocenters. All right, let's think about what those stereocenters are. So numbering, this would be number 1. This would be number 4. Right, this side here would be number 2, and that would be number 3. So that's moving around this direction. That is the R direction, but we have to change our answer to S because number 4 is pointing at us, so that's an S. And if we look over here, that's number 1. This is number 4. This is number 3. And up here we have number 2. So that's going around this direction. That is the S direction, but we have to swap our answer, so that now is R. Now, if we draw the mirror image of this thing, what do we get? So here's our mirror. It's a CH3, and now we have a CH3 down here below. Right, this is going to put an OH here, right? And then that's an H atom that's over here, and then across this we have an H atom here and an OH here. Now, if we go through and label the stereocenters of this, you get this as an R and this is an S. So at first you think, well, these are not the same. Different molecules. But what we're going to do right now is we're going to do a 180 degrees flip. So we're going to take this and we're going to flip it up to the top. We're going to take this and flip it down to the bottom. Okay. So what that's going to give us, because remember, we're allowed to do that with Fishers. We're going to get our CH3 down here at the bottom. But it's just going to move the position of our OHs. And we can see that these two molecules are superimposable with each other, right? And that changes this top to an S and the bottom down to an R. So this is an achiral / meso structure. Okay. The other thing that we've already seen is we've really seen the following too, but we've seen cis-trans isomerism. So here we have cis-2-butene. Remember, two atoms that are identical, one on each carbon. It could be the H's or the methyls. Or you have trans-2-butene. And then the same cis-trans applies in molecules too that are cyclic. So if we look down here below, here are cycloalkanes. So we have this first ring structure with 1,2-dichlorocyclopentane. This is the mirror image. So these are actually enantiomers of each other. They're non-superimposable mirror images. Okay. And this molecule over here, right? So here we have trans and trans. Here we have cis. So this is a mirror plane right here, which means that this molecule is meso. However, notice that we have two stereocenters. So we have a total of 4 maximum stereoisomers. So you just took care of 2, and then the third one is this guy right here. And that doesn't have an enantiomer. So the relationship between this and both of these guys, these are diastereomers of each other. right? So diastereomers are simply groups of stereoisomers that are not enantiomers of each other. That's all that means there. Right? Now, there's a couple other cases that come up too. Let's look at molecules with multiple stereocenters. So of course you can have more than one. So here we have molecules that have a bromo and a chloro on them. So what I've done here is I've drawn out our first structure. So notice the bromo group here, right, to the right, to the left. So this molecule, you can't do that 180 degrees flip from, otherwise your bromo and the chloro switch their positions so they don't lie on top of each other. So these are enantiomers of each other, right? And then the other thing we could do if we're just statistically trying to put them in different places is you could have a bromo on the right and a chloro on the left. And then this would be the mirror image of that molecule. And those are non-superimposable mirror images of each other, okay? And then the relationship between these two sets of enantiomers is of diastereomers. So they're diastereomers to each other. Now, that's the bulk of what we're going to see. There's a couple other little things that pop up, and you'll see them from time to time. So it is possible for a molecule to be chiral even if it doesn't have a stereocenter. And these are usually molecules that have a twisted or a helical structure or something that prevents free rotation. So there has to be some type of restricted rotation. So one of the classic examples that you see is two benzenes connected, but they're out of plane relative to each other. So it's like you have a playing card that you've taken and you've moved the other card 90 degrees and you're trying to jab them into each other, right? Or two plates that are 90 degrees from each other. Now normally you'd have free rotation there. So if you just had a molecule like this connected to a molecule like that, those two ends can swing around like paddles basically, right? But if we prevent that rotation by putting large bulky substituents, then we limit ourselves to that free rotation, right? So that molecule is chiral. What we've drawn here is the mirror image, and that is an enantiomeric set of two molecules, right? Of the same molecule, I guess. And again, if we had free rotation, you could rotate that around and make them superimposable, but you can't. In order to do that, you'd have to adopt this planar conformation here, and that just puts too much strain over these big two giant balloons that won't pass through each other. So the other system to look at is these chair conformations. It turns out they can be a little bit tricky. If you look at this, and this is pretty hard to visualize, but if you look at this first chair, right, we have our chloro group at carbon 1 and another chloro at carbon number 2. All right, and these are on the same side there, so they're going to be cis to each other. So this, what I've drawn over here, is the mirror image. So this is the mirror image of that structure. And this is the thing that gets hard, because it seems like if you rotate this thing around that they'd be superimposable, but it turns out that they're not. So no matter what type of rotation that we do, we cannot get both of these chloro groups to match up with these two chloro groups. It's possible to do this, but not without doing a chair-chair interconversion. So when you're looking at these chair conformations, I usually tell students, take it out of the chair and draw it out flat. And once you're looking at it flat, then you can make a better assessment as to whether or not it's the same as or different than a molecule that you're comparing it to.